Hello, welcome back. Today we're going to look at our second example of a network optimization problem. If you are not familiar with networks in the context of optimization and haven't watched the previous video, the video preceding this one, in which I talk about the transportation problem, please go back to that video and watch that first, because in there I'm going to touch upon some basic network concepts, the idea of nodes and arcs and all of that stuff, supply and demand nodes, etc. Please watch that first. Otherwise, if you are already familiar with these basic ideas and you just want to look at the assignment problem specifically, then just continue on. For those of you who want to see the transportation video, I'm going to add a link to this up here in the top right corner, and also a link in the description of the video below. All right, so the assignment problem can be seen as a special case of the transportation problem, and we'll see why in a second. But what is the context in which the assignment problem comes up? So it comes up when you're trying to create pairs of things or pair up something with something else. And there are several situations where this may come in handy. So for example, the example we're going to look at together in detail in a second is I have several jobs or tasks that need to be done, and I have a team of workers. Depending on the person, they have the ability to do maybe all tasks, maybe just some of them. And if I assign a worker to one of these tasks, there could be a cost involved. So like that worker charges this much to perform that task. A slight variation of this could be you have a company and there are several projects that you're going to subcontract, and there are outside companies bidding on maybe a subset of these projects, and you want to assign, and this is where the traditional restriction of the assignment problem comes in. The standard assignment problem is a one-to-one pairing. So you're going to assign one worker to one job. That is, a worker can only do one job. A job only needs one worker. Or in the case of the bids of the subcontractors, it's a one-to-one as well. If you wanted to do a many-to-one, there's some changes you have to make. But let's assume we're doing a one-to-one mapping. Other examples of this could be you're pairing up drivers with cars in a situation like that, or airplane pilots with planes. You could also be pairing up people with other people. Maybe you're creating, there are companies who do paired up programming jobs, so that one programmer watches the other one as they are coding, and that reduces the amount of mistakes they make. There is a whole sort of research done in this area. It appears to be beneficial. So whenever you want to pair things up together, you will think of the assignment problem. Great. So let's look specifically at what we have here. So as I mentioned, we have some workers and tasks, more specifically 5 workers, and I'm going to name them workers 1 through 5 according to this table, and 4 tasks or jobs that I'm going to name A, B, C, D. And let's begin with the numbers in this table, meaning the following. An empty indicates that the particular worker is not able to perform that task. They don't have the skill set, for example. And when there's a number, that means how many $1,000 the worker charges to complete the task. Worker 1 will charge you 10 grand to complete task A. And worker 1 can perform tasks A, C, and D. All right. Likewise, you have the data for the other workers. So your goal here is you want all tasks to be performed, and you want to minimize the total cost. Which workers do you assign to which task? Right. That's basically the idea. So in what way is this, related to the transportation problem? You can think of this as actually being a transportation problem in disguise. Remember, from the transportation problem, there were suppliers and consumers, right? The suppliers had things to give, the consumers want things. So the locations, in quotes here, right, are going to be the workers and the tasks. And the goods, again in quotes, that are moving in this network from location to location. What are they? Well, you can think of it as service, right? The worker has service to give, and the task wants service. So if I were to draw a picture similar to the one we drew with the transportation problem, I could do it this way. Let me open it here. I could put the 5 workers on one side, and remember the negative number means a supply, so each worker has a supply of 1 unit of service, meaning it can do 1 task. On the other side, I list the tasks as consumers or demand nodes who want, right? So the positive number is a demand. They want 1 unit of service. And the arrows here link a node, a worker node, to a task node if, according to the table, the worker can do that job. So you see there's no arrow from worker 1 to task B because worker 1 cannot do task B. So this unit of service that's sitting here in worker 1 can't be shipped to the task B node, right? Great. So now notice, if you just came into the room and you looked at this picture here, and I told you, oh yeah, these are 5 warehouses, each of which has 1 airplane sitting there, and these are 4 airports, each of which wants 1 airplane, and these are the possible shipping routes and cost, etc., you would totally believe me that this picture makes sense, because essentially it's the same thing, right? It doesn't matter what you're shipping. There are 5 supply nodes, each of which has a supply of 1, and there are 4 demand nodes, each of which has a demand of 1, and you want to move the goods. So this is just to say that the assignment problem is like a transportation problem in disguise, right? And if that's the case, we're going to see that the Excel model is going to be very similar to the transportation model. So let's take a look at that. Before we go into the sheet, let me just briefly remind you of what the math for this would look like. In class, we'll go over this more slowly, but for now, and if you're not my student, I at least want you to see some of this. So as before, if you recall, in the transportation problem, we had 1 variable per arc or arrow, because we want to find out how much moves from each node to each node. So I have an x1a, which is to say, did this unit of service move from node 1 to node A, in which case it would represent in the real life story that worker 1 was assigned to job A. So this is my x1a, right? But in essence, I'm just going to say, well, whatever the parts the suppliers has to be no more than what the supplier has, and whatever arrives to the consumer or the demand node has to be what they want. Now, in the transportation example, we had total supply equal total demand, so we wrote all constraints with equality to indicate all suppliers will ship everything they have and all demand nodes will receive everything they want. In this case, if you add up, there's 5 units of supply, 4 units of demand. So I can still say that all the demand nodes will receive what they want, and I can write all demand node constraints with equality, meaning what you receive equals 1 for every task node. But on the supply side, I'm not going to say, hey, what you ship equals what you have, because there is an excess of supply. In other words, in the context of the story, one of these 5 workers is not going to work, right? But I don't know a priori who that is. So I'm going to allow potentially for any of them to not ship their service to a task node, right? Which means I'm going to write for node 1, I'm not going to say these 3 shipments will equal 1, what you have. I'm going to say these 3 shipments out of node 1 will be at most less than or equal to 1. And the same is true for all the 5 nodes, and this is what we have in the, these first 5 constraints here, right? What the parts from node 1 to A, 1 to C, and 1 to D, the total shipments out of node 1, aka the outflow of node 1, is at the most what node 1 has. Because maybe node 1 is going to be the idle worker, I don't know. And likewise for nodes 2, 3, 4, 5, I'm just going to say what ships out of you is at the most what you have. For the constraints of the 4 demand nodes, A, B, C, D, I'm going to say, hey you, node A, whatever you receive from node 1 plus what you receive from node 2 plus what you receive from node 3. This is the total flow of goods into node A. Remember, goods here is the service. Equals what node A wants, which is 1, because I know there is enough. So I'm going to say equal 1 there. And for the objective, it's just like the transportation example. If you use a route for shipment, you pay the per unit cost. So however many units ship from 1 to A times 10. And we know that this answer is going to be either 0 if that worker doesn't do that task, or 1 if the worker does that task. Great, so that's the math. Let's go to the Excel. And like we did in the transportation example, we're going to make a rectangle, right? Basically, as many rows as there are worker nodes or nodes on the left-hand side of that picture, and as many columns as there are demand nodes or the nodes on the right-hand side of the picture. So just to confirm here, if I pick a cell inside this gray rectangle, it represents an X variable. Which one? This one, cell C7, is the variable that goes from node 3 to node B, right? It's the X3B. Great. If we go here to the picture, do we have X3B? Well, you'll see that we don't, right? And if you go back to the table, indeed, no, worker 3 can't do task B. So the math is not going to have an X3B, but I am putting an X3B here in the sheet. Why is that? Well, the reason I'm doing that is so that my life is easier formula-wise for Excel. You'll see why in a second. But because I am creating this X3B and it shouldn't be there, I'm going to have to do something about it later on. We'll see. But let's first start filling out the easy parts of this. So according to the math, what goes out of node 1 should be no more than what node 1 has, right? Well, the flow out of node 1, aka the outflow, as we calculated in the transportation problem, is just the sum of all the variables that begin at node 1 and go somewhere. 1 to A, 1 to B, 1 to C, etc. And again, if you go back to the picture, not all of these x1s exist, but let's assume for now that they do. Because notice, if I do that, this sum formula is the very same formula for every node. I don't have to be thinking, hey, do you have an arrow to node B? Do you have an arrow to node C? In which case, every single one of these formulas in column F would be different, which would be more work for me. So let's assume an arrow goes from any worker to any task for now. And if that were the case, we would simply say the flow out of a worker node is a sum horizontally like this, right? From a 1 to everybody else. And if I copy this, it's from 2 to everybody else and all the way to 5 to everybody else. Great. And then likewise, we're going to need to say that the flow of service into any of the task nodes equals what the task wants, right? But the flow of service into task A is whatever is coming from each of the 5 workers toward task A. So from 1 to A, from 2 to A. So we do the sum vertically like this. Again, very similar to the transportation example. Again, I am fully aware that not all of these arrows exist in the picture, but I'm pretending they do for now because that allows me to simply type this formula one time and copy through, and I'm finished. Imagine if I had, if I was pairing up 100 things with another 100 things. I don't want to be typing, hundreds of different formulas. If I type once and copy, it's much easier. Great. Now, the only formula missing besides the constraints is now the objective. Now, if you notice here, I have, the same data that was in the table, but I have these, what is this, 999 large number that I threw in here. Well, this is where I use this little trick to get rid of the arrows that don't exist. Let's go back to the picture. I'm saying, for example, there's no arrow from node 1 to task B. Worker 1 can't do job B. Right? So what I'm going to do here is when I do this sum product to calculate, remember, this objective function here, right? Every x variable times its corresponding cost. Again, like we did in the transportation example, every x variable times its corresponding cost, what's going to happen? I took each of the arrows that isn't supposed to exist and I artificially said to Excel that their cost is humongous when compared to the others. So this is saying, look, Excel, if you want to ship service from worker 1 to task B, that's okay. I'm giving you that variable, but it's going to cost you $1 billion. Well, it's not going to do it, right? So making this variable super expensive when compared to the others essentially is ruling it out from being used. And this is the trick that, forbids Solver from using a gray cell that I put up there and I really don't want it to use. Okay. You could also have done this differently. You could have created more constraints here on the side to say, hey, by the way, cell C5 has to be 0, right? But that's more work as well. It would be valid to do it that way if you wanted to. Great, so if we finish with this objective formula here, now we can go to Solver and fill this in. So the objective cell is where we have our cost, right? Because it's cost we want to minimize. The variables is the whole block of gray cells here. And the constraints will be, well, 2 groups. What the parts from the supply nodes, in this case the workers or the suppliers of service, is at the most how much supply they have. In this case, each worker has 1 unit of service to provide. And what arrives into the demand nodes, this is how many workers are being assigned to each task, should equal what they want. And again, in this case, each task wants 1 worker. Great. Make sure this is variables non-negative, and because everything is linear, we want to choose the simplex LP, linear programming solver. And let's click solve, right? All right, let's see, it should be done quickly. Great. Now let's take a look. First of all, let's look at all of the arrows that don't exist, which is the ones that I made cost 999. You'll see that if it's 999 here, there's a 0 there, meaning Solver isn't using that, which is what I wanted, of course, right? So the 999 trick worked. It's telling me it's going to cost you $21,000 to perform these 4 tasks. Let's see who's doing what. Task A, who is doing it? Well, wherever you see a 1, it was worker 3 that sent its service to task A. So worker 3 is doing task A. Task B is being done by worker 5. Task C being done by worker 1. And task D is being done by worker 4. And who is idle? Worker 2, right? Here goes. And it's $21,000 because the cost of worker 3 doing task A is 6, and worker 5 doing task B is 4, and so forth. And that adds up to 21. Great. In the statement of the problem, I mentioned that there is a easy slight variation of this, which is the following. What if the table I give you, right? We don't need this math part anymore. What if the table I give you represents not costs but quality of the assignment? For example, these could be scores from 1 to 10, saying the higher it is, the better quality is the result. So if I assign worker 1 to task A, it's a 10 out of 10. This person is going to do an amazing job. But if I assign worker 2, it's going to be a 6 out of 10, not as good. An interesting example of this that I sometimes mention in class is you could think of a matching website that tries to pair up people based on compatibility because they say they want to date. And these scores could be telling you how to suggest matches. So I suggest that you match person 1 with person A. That's a high score. Person 5 and person C, very good score as well. So what if I had this version instead of these numbers being cost? If they represent quality of the pairing, and I want to create the pairings that maximize the overall quality. Oh, very simple change, right? Because these now represent good things, I would flip, right, in my objective function. I don't want to minimize, I want to maximize. I want to make them as large as possible. However, be careful. Because I put these 999s there to rule out the variables that I don't want, if I simply just flip from min to max, the 999 now is going to be a fake representation that pairing is actually amazing, which is not the case because that pairing shouldn't even exist in the first place. So if you're solving the version of the problem that assigns quality to the pairings, what you need to do is to rule out a variable or arc that doesn't exist. Instead of using a large number, you use a tiny number or even a negative, right? You could put these, you could replace the 999s, for example, with a 0, saying there is 0 quality if you make that pairing, so don't make it, right? And these will be the only 2 changes for you to solve the quality maximization version of the problem. Okay, great. Other variations that I sometimes mention in class are, notice that they have some sort of flexibility here because you have extra workers. Maybe this is something that you do week over week, and you try to do some sort of balancing, and perhaps last week worker 2 was already idle, and it turns out that when you optimize for this week, the solver says worker 2 is idle again, and you don't want that to happen. So maybe you want to pick some workers and say, you know what? I want to for sure give a job to worker 2 because they already rested last week. And then let the solver pick what I assign to the rest of the workers. If there's some specific worker that you want to work, you simply would go in here and force that to happen. So for example, I could say, I want this number to be equal to 1. And if I add that in and solve again, it's going to find me the best answer that gives a job to worker 2. So you should wait a little bit. Oh, notice I clicked maximize. Let me go back because this is not what I wanted to solve. We're doing cost, right? So solve this again. Great. Now notice the following. I still got a 21, which is kind of nice because it basically says there was an alternative solution of the same cost as before that now made worker 3 idle and gives a job to worker 2. Okay? It didn't have to necessarily be the case that this new solution would cost the same. It just so happened in this case that it did cost the same. And if it didn't cost the same, it would also give you some interesting information. Let's say it was more expensive. Let's say it cost 22. It would basically flag to you the following. Hey, the need to give worker 2 a job costs you $1,000. What do you think of that? Right? So these are interesting insights that you can get out of solving these problems. But this is the assignment problem that I wanted to cover with you, and its little variations. As you can see, it's very similar. In fact, it's a special case of the transportation problem that we saw in the previous video. I hope this is helpful to you guys, and as I promised, I'll make another video that's network related, and now with those kinds of transshipment nodes that make things a little more interesting, and that's coming up next. I'll see you guys here again in the next video. Bye bye. Thank you for watching.